is by Dr. Kent Coulter from Sandia National Laboratories, and his paper is titled Surface Properties of Cobalt Silica and Cobalt Zirconia Silica Catalyst for Fischer-Tropsch Synthesis.
Thank you. My talk today is work that's been carried out at Sandia National Labs as a joint project between the Fuel Science Department and the Process Research Department. There are several people that I'd like to recognize. First of all, my co-authors, Alan Salt and Elaine Baseflood and Mark Harrington. I'd also like to acknowledge Steve Coulter and Nancy Jackson, who carried out some of the Fischer-Tropsch reactivity studies that I'll be briefly discussing. I'd also like to recognize Janos Sani and Mark Paffett at Los Alamos National Labs, who characterized some of the samples I'll be discussing using infrared spectroscopy. And finally, I'd like to acknowledge the National Renewable Energy Laboratories and the U.S. Department of Energy for sponsoring this work. In my presentation today, just about the only thing that's going to resemble the abstract that I submitted approximately 4 months ago is the title of the talk. At that time, we had very high hopes of using infrared analysis of CO adsorption on these cobalt on silica catalysts and the zirconia promoted catalysts as an analysis tool for identifying active sites, for identifying surface morphology, and also for looking at the promotion of zirconia on cobalt. Since that time, we've run into some unfortunate problems. The major one being that we cannot see adsorbed CO on cobalt on these samples. Here's a typical spectrum of 10 torr of CO on a reduced cobalt on silica sample at room temperature. All we see are features that can be identified as gas phase CO. We don't see any features at 2070 that would be identified with molecular adsorption on reduced cobalt. We also don't see a peak at around 2180 that would be assigned to the adsorption of CO onto an oxidized cobalt species on the surface. If we remove the CO from the IR cell, we don't see any features that can be identified as molecularly adsorbed CO on these cobalt on silica or cobalt zirconia promoted catalysts. Now, we've made several attempts at seeing molecularly adsorbed CO. We've cooled the sample, we've heated the sample, we varied the CO pressure, and after several very frustrating weeks where we were not able to see molecularly adsorbed CO, we sent these samples to our colleagues at Los Alamos. After 2 weeks, they called back, very frustrated, and said that they could not see molecularly adsorbed CO on these samples. Now, the fact that we can't see molecularly adsorbed CO is interesting, but we do make a couple of other observations. One is that when we introduce CO to these samples, we always see an increase in the background concentration of CO2. Now, this is in contrast to if we just introduce 10 torr of CO to the empty IR cell, we don't see this increase in CO2. We assign this to what's taking place is the Woodward reaction, where we have CO dissociation occurring on the surface of the catalyst, and we have recombination to form gas phase CO2. This is supported by XPS analysis of these cobalt on silica catalysts following exposure to CO. We see an increase in the amount of advantageous carbon on the surface of these catalysts. So what it suggests is that we do see a large amount of dissociation occurring on the surface of these catalysts. Another interesting observation that we make is if we heat these catalysts in the presence of CO and hydrogen, we see an increase in the peaks around 3,000 wave numbers that can be assigned to the formation of methane. So we are actually having CO interact with this cobalt on silica sample, and these samples are good Fischer-Tropsch catalysts, which I'll talk about in just a few minutes. Another interesting feature, though, is that when we do heat this sample at 250 degrees C in hydrogen and CO, we do see a large concentration of CO2, which would again suggest that the CO that does interact is dissociating either to form methane or to form CO2. Now, based on the observations that we've made of CO interaction with these cobalt on silica samples, we're able to make a couple of conclusions. The first one being that CO dissociation occurs rapidly on these cobalt on silica samples. Not only does it occur rapidly, but it occurs to a large extent. There are reports in the literature where they do see CO dissociation whenever they expose a cobalt sample to CO. But typically they also see some molecularly absorbed CO either on metallic cobalt or on oxidized cobalt that's oxidized during the CO dissociation. In this case, our samples, we see no molecularly absorbed CO. And from analysis of other samples such as nickel on silica, nickel on titania, platinum samples, we should be able to see around 5 to 10%. If 5 to 10% of the cobalt absorbs CO molecularly, we should be able to see it, but we do not. So there is a large amount of dissociation occurring. The second conclusion that we're able to draw is that the cobalt particles that we have are very rough and they have a large number of edge and step sites. This is based on our comparison with some of the reports in the surface science literature where they talk about CO adsorption on different crystal faces of cobalt. If you have a very rough surface, you have a preference for CO dissociation as opposed to a flat oriented cobalt surface where you more likely have molecularly absorbed CO on the surface. Now, the fact that we're seeing CO dissociation with these catalysts is not necessarily a bad thing. These are Fischer-Tropsch catalysts. So we want to dissociate methane as the first step. And as I said earlier, these are good Fischer-Tropsch catalysts. For a cobalt on silica catalyst, we get a CO conversion of about 80%. We get a methane selectivity, SiO2 selectivity, and an alpha number, or a chain growth probability, that agree very well with what's reported in the literature for cobalt catalyst. One of the interesting observations that we make, though, is that when we add a zirconia promoter to this catalyst, it's reported in the literature that you'll see an increase in CO conversion, and also you'll see an increase in selectivity to higher hydrocarbons. And we do not see this. There are a couple of possible explanations for this. The first one being that we have had some technical problems in our reactor studies. Therefore, a direct comparison of these two may not be valid, but we have run several samples of both the cobalt on silica and the zirconia promoted catalyst in a plug flow reactor and using a slurry phase reactor, and in general we see either no enhancement or very little, if any, enhancement by adding zirconia. The other possible explanation that we can use for not seeing this zirconia promotion is that in the preparation of these catalysts, it's possible that we did not utilize the promotional effects of the zirconia, such as intimate interaction with the cobalt or with the cobalt and the silica, in our preparation procedures. And for the remainder of my time today, I'm going to briefly discuss some of the observations that we've made on the dramatic effects of the surface properties of these cobalt catalysts based on very subtle things that you do during the preparation procedures. I'm going to talk specifically just about the cobalt on silica catalyst because we feel like if we can optimize utilization of the cobalt on these catalysts, then we can develop a zirconia promoted catalyst that will be even better. We prepare these catalysts using a basic recipe given in the patent literature. We use a commercially available silica support with a surface area of 300 meters squared per gram. We load the cobalt using incipient wetness impregnation of cobalt nitrate hexahydrate. Following impregnation, these samples are a bright pink color that can be associated with octahedrally coordinated cobalt. Now, in the patent literature, they discuss in detail the preparation and the impregnation of the cobalt onto the silica. After that, though, they state the catalyst was dried and calcined. They make no mention of the conditions that these were done under. In our experiments, following the impregnation, the samples were air dried at room temperature for 24 hours. Following that, we did an elevated drying procedure for a 15.8 weight % cobalt on silica catalyst. We dried it at 110 degrees in static air, and this is a mistake, it was dried for 6 hours. Following this drying step, the color of the catalyst had changed to black, which indicated that it had converted from cobalt nitrate to cobalt oxide. A second sample that we looked at was an 18.8 weight % cobalt on silica sample that we vacuum dried at 110 degrees C for 24 hours. Following removal of this sample from the drying oven, this sample had remained pink, which indicated that we did not have any nitrate decomposition that had occurred at 100 C in a vacuum environment. After the vacuum drying, an allotment of each one of these samples was removed for analysis. We then calcined them at 400 degrees C in air. Following calcining, these samples had a surface area of approximately 230 meters squared per gram, and they had a cobalt dispersion of around 5.8 to 5.7. So we had very large cobalt particles on the surface of the silica. Now, since our attempts at IR had not proved to be successful, the analysis technique that we chose to utilize was X-ray photoelectron spectroscopy analysis of these samples in an ultra-high vacuum chamber. This ultra-high vacuum chamber has a reactor cell connected to it where we introduce the sample into the UHV chamber by placing it in the reactor, evacuating the reactor, and then opening a valve so that we can lower the sample into the UHV chamber. Some of the samples that I'm going to talk about later will be referred to as baked samples. What this involves is that we heat the reactor at approximately 80 degrees C for 4 hours. We do this to remove any adsorbates that are on the walls of the reactor before we lower the sample into the UHV chamber. This is done typically when you're working with ultra-high vacuum environments just to maintain a low base pressure in the chamber, but it's typically not associated with any changes that you would see in the sample. Once the samples are in the UHV chamber, we anneal them in vacuum from 100 to 400 degrees C with an XPS analysis between each one of these anneals. We do this to remove any adsorbates that would be on the surface of the sample. Following this annealing, we then do a pre-activation treatment in either hydrogen or oxygen. A typical series of XPS analysis of the cobalt 2P region for a sample that's been air dried and calcined shows that for an as-prepared sample, we see a peak at 780 EV, and the peak position and peak shape indicate that we formed CO304 on the surface of this catalyst. If we then anneal the air-dried and calcined sample to 400 degrees C, we don't see any change in the peak position or the peak shape. We do see a slight increase in the overall intensity, and this is assigned to the desorption of the adsorbates on the surface where we have more where we have more cobalt surface area available to analyze. If we then reduce the sample at 250 degrees C, we see a shift in binding energy to 777.8 EV that's associated with metallic cobalt, and we get complete conversion of the cobalt to the metallic phase. This is supported by hydrogen chemisor oxygen uptake work on reduced samples where we do see approximately a 90% reduction in these samples. If we reoxidize this sample, we see a shift back to a peak position and peak shape that's indicative of the CO304. So we have an easily reduced cobalt oxide phase for an air-dried and calcined sample. Now, in contrast to this, if we look at the cobalt 2P region for the dried-only samples, for the air-dried sample, we see a cobalt 2P3 halves peak at 781.8 EV. In addition, we see these large shake-up features. The combination of these shake-up features and this peak position are assigned to cobalt nitrate, and this is not surprising since we've done no treatments to this air-dried sample. Now, if we take the same air-dried sample, put it in the reactor and bake it prior to lowering the sample into the UHV chamber, we do see a change in the cobalt features. First, the main change that we see is we see a decrease in the overall intensity. And this was very surprising because we did not expect the baking to affect the sample at all. But what we do see is that something as subtle as heating it to 80 degrees C will dramatically change the cobalt features. Now, if we look at the sample that was vacuum dried at 100 degrees C, 100 degrees C, we see the cobalt 2P features again that can be assigned to cobalt nitrate. We see an increase in the overall intensity of the cobalt 2P features, though, for this vacuum dried sample, and this is assigned to the fact that during vacuum drying of this sample, there's a redispersion of the cobalt nitrate on the surface of the silica, so we have a higher surface area of cobalt that we are able to analyze. If we look at a vacuum-dried sample that has been baked, we see a further increase in the cobalt 2P intensity, and again, this is assigned to further redispersion of the cobalt nitrate during this vacuum drying of the cobalt on silica sample. In contrast to the vacuum dried samples, the sample that was air dried at 110 degrees C, we see cobalt 2P features that are somewhat different. We see a slightly lower binding energy. We also see a decrease in the shake-up features. If you'll remember, whenever we removed this sample from the air drying oven, the sample had turned black, which indicated that it had turned to cobalt oxide. This agrees with what we see in the XPS spectrum, where we see a majority of the cobalt has converted to a cobalt oxide type of species. If we analyze the species coming off of the surface during the drying step with infrared, what we found that was for the air-dried sample, as it's being heated at 100 degrees C in a static environment, we see a peak at 1380 that can be identified as an NOx species in the near surface region. This NOx species can then oxidize the cobalt to form cobalt oxide. In contrast, for a vacuum-dried sample that's heated at 100 degrees C, we see no peak at 1380. Therefore, the NOx is not available to oxidize or to catalyze this reaction for the conversion to cobalt oxide, and it remains cobalt nitrate. Further supporting evidence for the fact that we have nitrate on some samples and not on others that have been dried is the nitrogen 1s region. For an air-dried sample, we see a peak at 407.4 eV that's assigned to nitrate. For the air-dried sample that has been baked, we don't see any nitrate features, which is somewhat surprising. We do see a peak at 399.8 eV that's assigned to residual nitrogen on the surface. So again, baking this sample appears to have fixed the cobalt on the surface of the silica. If we look at the vacuum-dried sample that was heated at 100 degrees C, again we see a very large nitrate feature. This supports the idea that we have a highly dispersed cobalt nitrate phase on the surface of the silica. The vacuum-dried sample again shows an increase in the nitrate features where we see more spreading during this baking process. And for the air-dried sample, we see no nitrate features on the surface of the catalyst, which is expected since this sample had turned black. Now, if we anneal these samples in the UHV chamber to 250 degrees C, which is well above the cobalt nitrate decomposition temperature, we do see a change in the cobalt features. For the air-dried sample, we see a decrease in the overall shake-up features, but we see that the binding energy remains at 781.8 eV. The fact that we see this high binding energy in combination that we're at a temperature above the nitrate decomposition temperature suggests that what we formed is a cobalt silicate, and the peak position and shape agree with those that are reported for cobalt silicate. For an air-dried sample that is baked, we see no change in the cobalt features. Again, this suggests that baking somehow fixed this sample. For a sample that was vacuum dried at 110 degrees C, we see the cobalt 2p3 peak at 781.6 eV. This suggests that we have this highly dispersed cobalt nitrate phase that is decomposed then to form a highly dispersed cobalt silicate phase on the surface of the silica. Now, the most unexpected result that we found was for a sample that was vacuum dried at 100 degrees C, baked, followed by annealing at 250 degrees C in the UHV chamber. For this sample, we get a 2p3 binding energy of 777 eV, which is well below any reported value for cobalt silicate or cobalt oxide. At this point, I need to clarify how we assign binding energies. These samples are typically exhibit charging. The way that we make corrections for this is by referencing to the silicon 2p peak for silica that is at 103.4 eV. By doing that, we typically have to make a charge correction of about 4 eV. By doing this charge correction, the cobalt, the oxygen, and the carbon peaks line up at the positions that we would expect for those species following the conditions that they've been exposed to. If we do this charge correction for the vacuum dried and baked sample, it shifts it to 777 EV. In contrast, if we don't make any charge correction for this sample, it shifts it back to 781 EV. And this is valid because if you look at the silicon 2P region for a sample that's been vacuum dried and baked and annealed to 250 degrees C, it's a very broad silicon 2P region. There are multiple peaks that can be assigned to the silicon, so it's very hard to make this charge correction. Anyway, if we do not make a charge correction, we see it line up right at 781 EV that would be assigned to a cobalt silicate. What we feel has occurred is that what we have formed here is a highly conductive cobalt silicate that is pinned to ground on the sample holder. The cobalt nitrate decomposed to form cobalt silicate that then covers the silica, contacts the sample holder, and does not exhibit any charging. Now, if we anneal this sample to 400 degrees C in the ultra-high vacuum environment, we see a shift back in the binding energy to a position that can be associated with charging. This is attributed to the agglomeration then of this thin film cobalt silicate into cobalt silicate islands on the silica that then will experience this charging because they are not contacted with ground. Finally, for the air-dried sample, we don't see any change upon annealing it to 250 degrees C. And this is expected because we had already seen that it had been converted to the cobalt oxide. If we look at the nitrogen 1s region, it supports the idea that we have had total nitrate decomposition. For the air-dried sample, we see no peak that would be indicative of nitrate. We do see some residual nitrogen on the surface. For the air-dried and baked sample, we don't see any change in the nitrogen 1s features from the as-prepared sample. For the vacuum-dried sample that was heated at 100 degrees C, again, we see no nitrate features as we saw with the as-prepared sample. We do see a broad peak that can be associated with some residual nitrogen remaining on the surface of the sample. The vacuum-dried sample, we do see a very small nitrate peak, but the intensity of this peak is order of magnitudes lower than the one that we had observed earlier. And this is probably just some residual nitrate that is remaining from this highly dispersed layer. And again, for the air-dried sample, we don't see any nitrate on the surface of this sample. If we go ahead and vacuum anneal these samples up to 400 degrees C, we don't see any change in the cobalt 2P or the nitrogen 1s features, except for the sample that was vacuum dried and baked, which I told you about earlier, where we see the shift in binding energy back to a charged position that's assigned to the agglomeration of the cobalt silicate. If we follow the 400 temperature vacuum anneal with a 400 degree reduction in hydrogen, we see very different amounts of metallic cobalt on the surface of these catalysts. For an air-dried sample, we see a very small peak at 777.8 EV that's assigned to metallic cobalt. The majority of the cobalt remains as an irreducible cobalt silicate species. For the air-dried and baked sample, we see even less metallic cobalt. The majority is an irreducible cobalt silicate. For a vacuum-dried sample that was heated at 100 degrees C, we do see a large fraction of the cobalt has converted to metallic cobalt, but again, we have a large portion that is in an irreducible cobalt silicate state. The sample that exhibited the highest concentration of reducible cobalt of any sample that we investigated, including the samples that were calcined, is a sample that was vacuum dried at 100 degrees C, baked in the reactor, vacuum annealed to 400 C, followed by reduction at 400 C. On this sample, we see a metallic cobalt feature that is an order of magnitude larger than any other sample that we investigated. Now, we do see a large portion of irreducible cobalt silicate on this sample, but the size and the intensity of this metallic feature far outweighs the small amount of cobalt silicate that we observed. This was a very unexpected result, that if we anneal a cobalt nitrate sample in an ultra-high vacuum environment, followed by reduction, that we could get a very large concentration of reducible cobalt metal. For the air-dried sample that was heated at 100 degrees C, we do see a large fraction that's converted to metallic cobalt, but the overall concentration of the metallic cobalt is very low. The fact that we are able to get this high concentration of cobalt surface area on the vacuum-dried, vacuum-annealed sample is supported by hydrogen chemisorption work. If you will recall, for these samples that were dried, followed by calcining, and then reduced at 300 degrees C, we get a cobalt dispersion based on reducible cobalt of around 5.7 to 5.8. If we compare this to a sample that was vacuum dried, followed by vacuum annealing, we do no calcining, we then reduce it at 400 C, which is 100 degrees higher than the other samples, and a higher reduction temperature is typically associated with sintering of the metal. What we actually see is a doubling. It increases by a factor of 2 the cobalt dispersion based on reducible cobalt. This is even though the percent reduction of the sample decreases, the amount of reducible cobalt surface area that we have has doubled for these samples. Let me go ahead and conclude. The first conclusion that we're able to draw is that the drying conditions strongly influence the final state dispersion and reducibility of a cobalt on silica catalyst prepared by incipient wetness impregnation of cobalt nitrate hexahydrate. From our experience, what we've found is that the steps that you take in drying these catalysts have a much more profound effect than, say, any promoter that you could add to the catalyst. And this was somewhat surprising because typically in heterogeneous catalysis literature, they do give a detailed description of how the catalyst is mixed and how the cobalt is deposited, but they do not discuss in detail how it was dried. They say the catalyst was dried, or the catalyst was dried in vacuum, but they don't state the actual conditions that those were, and those seem to have a profound effect on the available cobalt. The second conclusion that we're able to draw is that the concentration of NOx species at the surface of the catalyst during the precursor decomposition determines the nature of the cobalt phase. For the samples that are dried in air, there's a large concentration of NOx at the surface of this catalyst during the decomposition that allows the cobalt to be oxidized and form these large particles that are easily reduced, but it does not optimize your use of the cobalt metal. In contrast, if you vacuum dry these catalysts so that the decomposition occurs in an environment where there are not these NOx species, then you form a cobalt silicate which under the right conditions can be reduced to form a highly dispersed cobalt phase on the surface. The final conclusion we're able to draw is that the highest concentration of reducible cobalt surface area is for a sample that is vacuum dried and vacuum annealed at 400 degrees C. Now, I realize that in most heterogeneous catalysis labs, they do not have the capability of placing a large batch of supported catalyst in a UHV environment and annealing it to 400 degrees C. But what I think that this indicates is that there should be further work in the area of using maybe alternative methods in drying and calcining these samples so that we can then optimize the use of our cobalt before we ever add any promoters to the catalyst. Thank you.
Do we have questions? Yes. No.
Alabama, Penn State. I just thought I mentioned that we have prepared iron catalyst requirement using a triiron needle and found similar behavior in the sense that if you expose it to CO and evacuate, there is no residual integrated chemical CO. And I wanted to mention also that wire is reported on certain iron crystals. You can get CO, they claim you can get CO chemisorption in a side-on fashion by virtue of essentially use most of your surface dipole. Now my question is, have you done CO chemisorption on these catalysts that did not show an infrared band? Because we found huge CO chemisorption values, but no infrared detectable CO.
Yes.
I presume you found the same.
We did. Now, I will say we found CO chemisorption, but it was in very, very small amounts.
It was small in your case.
Very small in our case.
Well, the question is, can you completely discount the possibility? I was curious about the updates because
Right.
Can you discount the possibility that in addition to, or maybe in lieu of, the association, I should say in addition to, because you're definitely.
Right.
You might have some CO adsorbed in such a fashion that it would be infrared active.
No, I agree totally. I feel that there is very possibly CO absorbed in a way so that it is not IR active. But at this point, we had intended on using IR.
Yeah, Keith?
Just to follow up on Al's question, I take it these times when you don't see CO absorb, these are taken at room temperature.
The spectrum that I showed you we also did some at low temperature.
That's what I was going to ask you.
Yes.
Do you find the same observation at low temperature?
Yes, we do. We are only able to go to about minus 100 C.
You don't say it then.
We still don't see.
So, this is sort of supports Al's idea, because at low temperature you wouldn't expect this, to dissociate CO so readily.
That is true. Just recently, there have been some reports in applied surface science where they looked at CO adsorption on polycrystalline cobalt. They didn't use IR, but they used XPS. And it's true where they did see, and there are other reports of this too, where you do see molecularly absorbed CO at these lower temperatures. But even in those cases where they did it on a polycrystalline foil, it was a very low concentration that they were able to see, at least in the temperature ranges that we were able to get to.
Well, we used to do chemisorption measurements on cobalt Fischer-Tropsch catalyst before infrared came along. We got substantial chemisorption.
Yes. Now I want to make that point that, I mean, there are definite reports in the literature of cobalt on silicate catalyst where they see IR adsorption, and there are ones where they see a large amount of CO chemisorption. Something that we have done in our preparation steps, we feel there is something about these samples where we do not see large concentrations.
Yeah, Norman?
I don't know, what do you have in mind for NOx? I mean, if somebody showed me a spectrum with a band of 1380 and they say it's NOx, I'd say it's NO3, it's not trade.
I'm basing that reference on a paper that came out in, I believe it was Thermochemical Attica by Mansur, where they looked at cobalt nitrate hexahydrate decomposition. They didn't do it on any type of support. And they assigned a peak at 1380 that would be assigned to an NO3 type species, but it was a gas phase species.
Oh, I see.
Yes.
A gas phase.
It was a gas phase NO3 type species.
Yeah, John?
What's NOx doing? What's your thought about that? Is there something magic about NOx, or could someone of anion do this?
That's something that we're investigating using different types of precursors. The way that we actually came on to this idea was based on some work that was done on cobalt on alumina, where they suggest that the concentration or the dispersion of the cobalt that you have on the surface of a support is determined by whether or not it can be oxidized during the decomposition process. And they state that in large concentrations of NO2, which oxidizes extremely well, you will get this formation of these large particles of cobalt. Some of the things that we've been interested, or we are going to pursue, are the use of like a cobalt chloride precursor or a cobalt carbonate precursor, and to see what effects then the removal of those types of species have on the overall final state of your cobalt. But we feel like that the NOx oxidizes, specifically the NO2 oxidizes the cobalt.
But you're not suggesting, are you, that the anion containing the cobalt, if I can use that expression, is determining the initial dispersion?
What I am suggesting is that the conditions that you utilize, even the fact that after mixing the sample, placing this cobalt precursor onto a type of support, the steps that you take after that determine and even the fact that if you leave it in air for, say, 2 or 3 days, I think has a tremendous effect on your final reducibility, as opposed to, say, taking that wet catalyst and maybe then placing it into an environment where you can remove a large amount of these decomposition products. Another thing that we're looking at is not necessarily using a UHV environment, but doing it in a place where we have a high throughput of an inert gas, where we can remove these decomposition products during the heating.
Well, thank you very much for a very interesting presentation. I think we should thank all of our speakers for this morning for giving us an interesting discussion. And we will reconvene then at 1:30 this afternoon when Keith Hall is going to tell us about Bob Eichen's career.
Yeah.